I'm audible on YouTube.
I'm audible on.
So when you define a force, okay. So I mean, while doing that, I mean, you have calculated work done in two different ways. Am I right? For this one, let me take this one. Okay. One is we define force like this. This is equal to 1 by 4 pi epsilon naught. Speak up. Q square divided by 2z the whole square. I mean, suppose they were at arbitrary distance. Okay. Speak up. They were at arbitrary distance 2z. And they're, I mean, from infinity, you are just moving them here. Okay. So minus z cap, isn't it? When they were at arbitrary distance. Now I will I mean, this is the force on this charge. Am I right? Let me take the arbitrary situation. Okay. This is at plus q at at a distance z, minus z here, or again a z here. Okay, minus q somewhere here, minus q here. Is that okay? Speak up. That is one arbitrary situation. Now that z was infinity, I made it z equal to d and d. Okay, speak up. So then if I write force at any instant of time, that's equal to 1 by 4 pi epsilon naught. Speak up. Q square by 2z the whole square minus z cap. Am I right? Speak up. Now while I'm writing this force, okay, I'm writing force on plus q charge. Am I right? I'm concentrating only on this one. Okay, speak up. And if I find, any question? Yeah. So if I find work done in order to move this plus q charge, okay, from infinity to distance d, okay, speak up. If I'm using this force means, look at, I mean, I need to place one more negative sign because I need to do work against the force, okay, infinity to what you call d, f at plus q charge dot dl vector, okay, and we found that this value, isn't it? Pick up. What was this value? Pick up. Minus 1 by 4 pi epsilon naught. Speak up. Q square divided by 4 into d. Am I right? We found it like this. Now, while doing this one, look at here. You are concentrating only on force on plus q. Okay, who is moving this minus q? Look at here. At each and every position, this minus q is symmetrically situated below, isn't it? At minus z. Are you getting the point? I mean, while integrating, you are changing z. Am I right? When you move this one, this is also moving here. When you move this one, this is also moving here, isn't it? Pick up. Who is moving here? You have taken work done in order to move this one only, isn't it? Speak up. So there is no work done calculated. I mean, in order to move this one, isn't it? Pick up. That is the right way to calculate, because in the actual situation, when you move this charge, whatever the work done in reassembling this free charge carrier on a conductor, that is zero actually. So that's why this gives the right answer. Okay, this gives the right answer. But we don't want to what you call do this integral always. Suppose this is okay. This is very simple problem. If suppose there are conductors like this, okay, speak up. I mean, infinite conductor which are perpendicular to each other. If you place one charge q here, then you have to take image charges. Then there will be 3 more charges comes as an image charge. Okay, speak up. In that kind of problem, line integrating that force would be quite difficult because the net force will be in some arbitrary direction. Okay, speaker. So that's why you better to what you call. I mean, this is the right way. Why this is the right way? Because you calculated only work done in order to move from this one. And look at here. Just like this charge is going from infinity to this one simultaneously when you move from positive to infinity to this one, these charges are also building up like this. When it is very far away, no charge. When it's moving slowly, these charges are building up, isn't it? That's why the way that we have calculated this one is the right one, because when you move this one, this force says this also moved to minus infinity, isn't it? Speak up. That means when you move this one to infinity, no charge density here. A return point. So that's why this is the right way to calculate the work done, but I mean we don't prefer, okay? I mean to line integrate and all. So now what we do is, speak up. Now the difference is work done. I mean what I do here is again in the second method of finding the work done, okay? So what I do is I'm going to pick up. Suppose this is plus Q. Pick up. This is minus Q here. Speak up. D here minus D here. Okay. Speak up. Now in this one, what we do is we first place minus Q and we fix it there, isn't it? I mean, in other way, while finding the electrostatic energy, isn't it? We place it minus Q from infinity to this point, and this is at rest here, isn't it? Then we find work done in order to move this one from infinity to this point at a distance 2d from this minus Q, okay, by fixing this one, am I right? This situation is very different from earlier situation. In earlier situation, just look into the force. Force is calculated by 2z, am I right? I mean, these two are moved together actually in the earlier situation. These two are moved together, and you calculated what you call force, what you call work done in order to move the one of the charge, isn't it? In the earlier calculation, so you have taken the force due to this charge, which are symmetrically situated, and you have taken the situation where these two charges move together. But here you place one charge, okay, and there is no work done in order to place this charge when there are no other charges. Then you start placing this charge, am I right? That's the way you calculated the what you call for any point charge distribution. That's the way you calculated the what you call net electrostatic energy, isn't it? Speak up. So that's why this is Q into potential at Q, isn't it? That's how we have written. Speak up. That's equal to plus Q into what is the potential at Q? 1545 epsilon naught. Speak up. Minus Q divided by 2D. Am I right? Speak up. Potential at this point, isn't it? Speak up. That was equal to, speak up, 1 by 45 epsilon naught, okay? Minus Q square divided by 2D. Speak up. But this is not the right one. Because here we took this charge is at rest and this charge moved from infinity to this point. There is no work done in order to place this charge, okay? This charge is at rest and this charge is moved from infinity to this point. Speak up. One thing. So that's why this is not the right work done, okay? This is not the right work done. So actually what will happen is when you move this charge from infinity to this point, these charges are slowly built up. A return point. So that's why earlier one is the right way. This was also at infinity, this was also at infinity, both are moving together. That was the right way to calculate, okay? But now forget about that force integral for a time's sake, okay? You just think this is very easy to calculate for any point charge distribution, for any image charge distribution. How to get answer for this one? This is the actual one, am I right? Pick up. This is the trick. I mean, to find the potential above and all, isn't it? Pick up. How to find the work? I mean, electrostatic energy for this configuration, okay? Because again, for point charge distribution, this is the very easy way to calculate the total electrostatic energy. That's right. For this point charge distribution, this is the total electrostatic energy. But look at here. In this configuration, below the plane also have got electric field, isn't it? Pick up. But in this configuration, only above the plane you have electric field, okay? Below the plane you have zero electric field. And if you think about only, forget about the direction of the electric field, if you think about only what you call this electric field strength magnitude is square and all, that contribution is same, right, below the plane and above the plane, or whatever the number of field line you draw below the plane, number of field line above is same, isn't it? Speak up, because it's quite symmetry about xy plane. The charges are symmetrically distributed, isn't it? Speak up. So, but in this situation, there is no what you call field below. Is that okay? That means, so find again. So take this answer, okay, electrostatic energy due to this one, and divide that one by 2. I mean, you just removing the below part, okay. While doing that one, we are looking into this formula: epsilon naught by 2 integral of e squared d2. Am I right? Speak up. So here that is half of the total region. Here that is full region, isn't it? Speak up. So that's why the basic idea here is you calculate like what you have done for point charges by assembling the charge. First charge, no work done. Second charge, work done. Third charge, work done due to these two, isn't it? Like that. You calculate like that. And then after that, think over it. I mean, what is the region of the total space which is linked with the electric field, which have got electric field? That is half compared to this one, isn't it? Figure. By looking into this formula, I'm going to guess that I'm going to what you call argue that okay, work done in this actual situation. This is actual. Can I write like this? Or actual electrostatic energy stored, that's equal to speak up half of that one. Half of 1 by 4 5 epsilon naught speak up minus q square by 2d 1 by 4 5 epsilon naught speak up minus q square by 4d. This is what we got by integrating the force. Speak up. So only in this situation you have to be careful. Force also you can find using image configuration. Okay. So potential you found using image configuration. Okay. If you take the gradient of the potential, you get the electric field. Speak up. But while finding the work done, okay, find the what you call electrostatic energy stored here. Okay, think. I mean, what is the region compared to this one? What is the fraction of the region which have got electric field here? That is half. Because exactly other half is cut off, and by looking into this kind of equation where integral over all space where you have electric field, am I right? Pick up. This equation integral over all space, am I right? Here you are integrating here also downward as well as upward to xy plane, isn't it? So here you need to integrate only above, below electric field is 0. That's why it should be half of this one. Okay, so remember this argument and find it like this. Okay, this will be helpful when I give two what you call infinite perpendicular plane and one charge is placed in that situation and all. You can take whatever the image configuration and you can divide by fraction of the region which have got electric field, and you will get the right answer. Is that okay? Only while finding the work done you should be careful. Okay. Now, in this image configuration, there are many nicely designed questions are there. Okay, suppose if it is released from rest, it's going to hit the plane. Am I right? With what velocity it's going to hit the plane? Speak up. Or if it is released with some initial velocity, with what velocity it's going to hit the plane? So you have to apply conservation law. Speak up. Or at what time it's going to hit the plane? Lot of questions are designed. I mean, one thing is you have force here, am I right? So using that force, you can find somehow you can relate it to time while integrating it down. Newton's second law. Okay, speak up. So lot of question can be designed here. Okay, I mean this is very basic part. Whatever I have explained here, questions are there on this one also. Surface charge density, these things. Okay, but I mean, if you see TIFR and just question, they will what you call you have to use the answer and then you have to do something else. It will hit the plane because force of attraction is there. In any induced charge, there will be force of attraction. It's going to hit the conductor. Is that okay? So when it hit the conductor, suppose initially it has some what you call potential energy. When it hits the conductor, that purely converted into kinetic energy, isn't it? Like that. I mean, somehow conservation law like that. Okay, that kind of problem I doubt that Griffiths have mentioned. He didn't mention. Okay, because see TIFR and just question on this particular topic, okay? And I'm going to release this one, okay? And at what time it's going to hit this one? The distance is given, d is given, charge is given, like that. Then you need to integrate force, you need to find the velocity, then again you need to integrate, you need to find the time and all. Is that okay, speaker? Yeah. Now let me move on to this example 3.2. Now solve corresponding problem, problem 3.7, okay, and problem 3.10. You can guess that one. Try that one, okay, as much as possible. 3.10, 3.11, and you need to do 3.11 with all care, okay. Pick up. I mean that contain one generalization also. Generalization. I mean at what situation we can use this image method, okay. Speak up. Now, have you observed in this situation, okay, whatever we have done, the first image, what you call problem, where did we place the charge? Below the plane, am I right? Speak up. That was not our region of interest, isn't it? You are only allowed to, I mean, while solving the Poisson equation, okay. So, what was the boundary condition on xy plane? You are potentially equal to 0, and you have one charge above. Am I right? Potential at boundary is now, charge density is now. Am I right? Pick up. You should not disturb that one. You can place the charge anywhere else, image charge anywhere else. You should not disturb that one. You are not allowed to place the charge in the region of interest. If you place that one, then it's a different Poisson equation. Speak up. Del square V is equal to minus rho by epsilon naught. Okay, speak up. Rho is different now. In the region of interest, okay, you should have the same type of charge distribution in the actual problem and in the image configuration. That's why we safely placed that image charge below the plane, which was not our region of interest. I mean, above the plane, still the same Poisson equation was satisfied as earlier, isn't it? Pick up. Now look at here. So this is example 3.2. Example 3.2. Speak up. Speak up. I have a sphere, okay. So conducting sphere of radius capital R, okay. So sphere made up of conductor of radius capital R, which is grounded, okay. Potential equal to 0. Is that okay? I have placed the charge. Speak up. So plus Q here at a distance A from the center of this one. At a distance A from the center of this spherical conductor. Okay, so conducting sphere, and it's potentially equal to 0. V equal to 0. Okay, V equal to 0 means it is equipotential. Okay, is that clear? Okay, you have a spherical conductor. Speak up. You have a spherical conductor, and you have placed one charge Q here. It is grounded spherical conductor of radius R. You have placed the charge Q at a distance A from the center of the spherical conductor. Is that okay? Because now we need to find the potential at any point here. Okay. So let me take this one as the origin usually. Okay. Potential at any point. Okay. Maybe you can take X, Y, Z, or you can take polar coordinate. That's also better sometimes. Okay. You can find the potential at that point. Again, you have to find the potential at that point using image method here. Okay, speaker. Now look at here. What are the situations here, boundary condition and all? On this region of the surface, potential equal to 0. Inside region is not our region of interest. Speak up. Our region of interest is only outside the conductor. Speak up. If potential is 0 on the surface of the conductor, inside potential is 0, isn't it? There is no charge. We didn't place any charge there. Okay. So, but inside region is not our region of interest. You are free to place charge there. Image charge there. image charge should be inside our region, which is not of our interest. Our region is outside, am I right? Because whatever you are seeing, there's a conductor charge outside region. That's what you are seeing here. Is that okay? Speak up. You need to find potential at this point, okay? Speak up. So then, look at here, what we do is we replace this one by an image configuration, okay? Speak up. That image configuration is such a way that is that same size sphere? No. Is that okay? Speak up. So, I mean, I'll just remove this sphere, okay? Speak up. This was the center of the sphere. So this Q charge is at the same point as earlier. Speak up. It is at the same point earlier, somewhere here. Speak up. Q is here, okay? This was R. Now, since this is not our region of interest, you can place the charge here. Let me place, I don't know where I need to place the charge here. Earlier, I can guess, am I right? To make XY plane zero potential, I place the negative charge symmetrically below, isn't it? But here I don't know, okay? What makes, what is the position of this charge? What is the amount of this charge? So that, what is the boundary condition here? On the spherical surface, your potential is zero. At infinity, potential is zero. Isn't it? And you have one charge here. Now I'm going to replace it by image configuration. So I have to place Q prime in the region not of our interest. Okay, there you can place the Q prime. So then, so that Q prime should make the potential on the surface zero. Is that okay? And Q prime, these are finite charge distribution. At infinity, potential is already zero. I have to place Q prime in such a way that image charge, we say image charge, in such a way that potential on the surface of this sphere becomes zero. Then these two in the outside region have the same boundary condition, have the same what you call charge distribution. Can I say like this? That's why Poisson equation is same in these two outside the region, okay, not in this region. Inside this region, both are different. In the earlier image problem also, below the plane, both were very different. Figure. Inside the region here, actually, potential equal to zero because we didn't place any charge inside the conductor. Speaker. But in this region, you place the charge. Inside the region, potential is altered. But our idea was not to find the potential inside, speaker, in the actual problem. It is to find the potential outside. Okay? For potential, for any point outside, okay, the if you see Poisson equation, okay, we are going to place this Q prime in such a way that potential on the surface of the surface. Now this is an imaginary surface. Now I just removed the conductor. So I will place Q prime in such a way that I will choose the Q prime, the magnitude of the charge, and I'm going to place it in such a way that potential on the surface of this region is equal to zero. Then both will have same charge configuration, same boundary condition in the outside region. Is that clear? Now, at this point, this is the point on the conductor, am I right? Because this was also point on the conductor. And again, I'll call this one as A, this one as B, okay? Speak up. This one as A, this one as B, okay? Speak up. I'll say this Q prime is placed at a distance B from the origin or center of the sphere. Is that okay? Speak up. So this is at a distance A. This Q is at a distance A from the origin. Is that okay? Speak up. Just see this carefully. That okay? Q prime is placed at a distance B. I need what is the B, what is the magnitude of Q prime. I have chosen that one arbitrarily. The given quantity is A, Q, and radius, isn't it? Pick up. B, that what I have defined now. Okay, Q prime is what I have defined. Now you need Q prime, you need B. To find that one, what we do is potential at this point is zero in this situation. That's why this situation should also have potential at A should be zero. Potential at this point was zero. So again, in this situation also, potential at this point should be zero. Now I'll calculate potential at A due to Q prime and Q equated to zero. Potential at B due to Q prime and Q equated to zero. Two equation, two unknown. I'll find B and Q prime. B and Q prime are unknown. Okay. What is B? What is Q prime? Pick up. What is potential at A? Pick up. It is at a distance B plus R from Q prime. Pick up. 1 by 4 phi epsilon naught. So Q prime divided by B plus R. Pick up. This point is at a distance A plus R from that Q. Pick up. Plus 1 by 4 phi epsilon naught Q divided by A plus R. Pick up. Equal to 0. One equation I got. 4 phi epsilon naught you can cancel out. Okay. Pick up. Other equation. Potential at this one. Okay. Due to Q prime. What is this distance? Radius minus B. This distance. This distance is radius minus B. Pick up. So that's why potential at B is equal to 1 by 4 phi epsilon naught. Pick up. So Q prime divided by radius minus B, R minus B. So plus 1 by 4 phi epsilon naught Q divided by this Q is at a distance A minus B. A minus B? No. I mean, wait a second. At this B we are finding, am I right? This distance. Distance of this charge. A minus R. Am I right? Pick up. A minus R. That's also equal to 0. Pick up. That's why you got these two equations. Q dash divided by B plus R. Okay. So plus Q divided by A plus R is equal to 0. Pick up. So Q dash divided by R minus B. Okay. Plus Q divided by A minus R is equal to 0. Pick up. Two equation, two unknown. B and Q prime are unknown. Pick up. Q dash divided by B plus R, Q divided by A plus R. Q dash divided by R minus B, Q divided by A minus R equal to 0. So can you do it? Let me write it directly. You solve for Q prime, you substitute into other and solve for B. And substitute back that B, you solve for Q prime. Two equation, two unknown. Is that okay? So then you will end up with this one actually. B will be equal to, I think, R square by A. Q prime will be, obviously you can guess Q prime should be negative. But what is the magnitude net? That's not minus Q here. If this Q prime is minus Q, that will not make this sphere a spherical surface zero potential. Okay, its magnitude, again, you have to find using these two equations. That's equal to minus only minus R by A times Q plus Q. Is that okay? Pick up Q prime and B. If you place minus R by A Q charge at a distance R square by A from the origin, from the center of the sphere, then that will make this spherical surface zero potential. Is that okay? It's quite.
Sir, I have a question. Why don't we just place a charge of minus Q to the left of the origin at a distance A?
Wait a second. Look at here. You are not allowed to place the charge in this region. This is our region of interest where we are finding the potential.
It has been there.
Is that okay? Speak up.
Yeah.
Image charge should be placed only in the region which is not of our interest, because remember our ultimate aim was to solve this equation del square V is equal to rho by epsilon naught. Speak up. Minus. What is the region of our interest? Outside this conductor. In that region, this equation should not be altered. In that region, this equation should not be altered. Is that okay? Speak up. That's why you can place the image charge inside that one, not outside. Okay? Speak up. And inside, potential is changed actually compared to this one. Who worries? Okay? Speak up. Only outside region, boundary condition is same, charge distribution is same in the outside region. Okay? Boundary condition means this is the boundary actually. This was the boundary of the outside region actually, and infinity is other boundary. Speak up. So that's why the solution, whatever you get it from this configuration, should be same as that you get it from this configuration. Isn't it? Now look at here how difficult it is to find this surface charge density and then using that surface charge density to find the potential. Speak up. So hard. Is that okay? Now look at here. Now, so at this point, okay, I'll call this one as R prime. I'll call this one as italic R prime, italic R. Pick up. Potential at P, okay, that's equal to 1 by 4 phi epsilon naught. Pick up. Q prime divided by italic R prime plus 1 by 4 phi epsilon naught. Pick up. Q divided by italic R. Okay, pick up. This distance, okay, pick up. Where Q prime is given here, minus R by A times Q, okay. Now, what are these magnitudes of I mean, in problem 3.8, you need to write this one in a spherical polar coordinate. Okay, pick up. You need to write this one in a spherical polar coordinate. Cartesian is not so comfortable. Okay, what you can do is you can choose your z axis along this one, and when you rotate the system about this one, you have symmetry, isn't it? Are you grabbing my point? Choose your z axis line joining this one, and rotate this one. Even though there exists a charge distribution minus and all, that will have one azimuthal symmetry actually. Pick up. So in that case, you can write, I think, potential in terms of r and theta alone, independent of z. Okay, can you think of it? Speak up. Inside this one, yeah, definitely inside everything is changed here. On this one, it is same as this one. Okay, speak up. But our region of interest is outside. See in the perspective of outside. On this boundary, you got the same potential, and at infinity, potential equal to 0, and you have only one charge in the region outside. Speak up. That's not disturbed. Speak up.
Taken as region that is not of interest.
I mean, this is the region not of interest. Am I right? We are not looking into potential inside this one. Am I right? That's why you are free to place the charge there. Okay. That definitely your Laplace equation is altered. Here it is Laplace equation. Now here again Poisson equation in this region. But it is not our. It is not of interest. Speak up. Now, can you find the force on this one? How do you find that one? Force. Let me rub out these things. Quite distractive. Speak up. This is B. This is my origin. Okay, this is B. Let me draw one line here. This is Q prime. This is R prime. Now, usually our point of interest will be this is R prime. This is R. Our point of interest will be usually this is A. Am I right? Speak up. This is actually R vector. Can I say like this? From the origin, field point is R vector, isn't it? Pick up. From the source R prime and R. Two sources are there. Okay. Pick up. So can you find R prime and R in terms of this italic R? What is this one? This distance is A minus B. This is A. This is B. This is A minus B. Speak up. Hmm? 。 That's not required in the spherical polar coordinate. I think I can directly write, but still I need that one. Okay, still I need that one. So can I define this one as R1 prime? Pick up. And this charge as R2 prime. R2 prime. Pick up, because you have two charges here. I mean, that prime coordinate we use for source charge, am I right? From the origin, okay? This is R. This is italic R prime. Pick up from source to field. This is italic R. Speak up. Can you write italic R prime and italic, or I'll write italic R1, R2. That's better. Is that okay? Speak up. I'll write R1 here, R2 here. That's better. This is R prime vector, R1 prime. This R2 prime. Is that okay? Location of this one with respect to this origin. And what is italic R1? Speak up. Italic R1 is R vector minus R1 prime vector. Am I right? Pick up. R vector minus R1 prime vector, isn't it? Pick up. Italic R2 vector. Pick up. That's equal to R vector minus R2 prime vector. R vector minus R2 prime vector. Pick up. Or you can work out this law of what you call vector addition. Okay. Pick up. This is R2 prime from the origin. Okay. Speak up. You got this geometry? From this origin R2 prime, from this origin R1 prime, italic R1, italic R2. I took this one as first charge, this one as second charge, whatever, okay? Pick up. Now you have to place it here, okay? So this one is R1 and R2 here. Q prime is first charge, Q is other charge. Is that okay? Pick up. Now, what is this magnitude of this R1 and R2? Can you guess? You need this angle actually, this angle. If you define this angle, speak up. R and R1 prime, R and R2 prime, they have same angle. Am I right? Speak up. You know the angle between them? What is italic R1? That's nothing but, look at here, root of, speak up, R square plus R1 prime square, speak up, minus 2 R1 prime, cos of the angle between them. Speak up. What is R1 prime? Magnitude. That's nothing but B. That's how he has written everything in a polar coordinate. That automatically become polar coordinate. This is R. If this is theta, you take this one as z axis. Speak up. Can you work it out? This italic R1 magnitude, that's equal to law of cosine. I'm applying law of cosine. Speak up. That's equal to root of R square. Okay, keep it as it is. R1 square, that's nothing but B square. Okay, plus B square minus 2BR. Okay, into cos theta. Okay, speak up. Similarly, italic R2, that's equal to root of, speak up, R square plus R2 square. What is R2 square? That's A square. Okay, R square plus A square minus 2AR and cos theta. Angles are same. Okay, this is R2 prime. This is R. This is R1 prime. This is R. Angle between R and R2 prime, R and R1 prime. Both are same. Speak up. This is what he has done. If you take this one as now Z cap, okay, just rotate it if you are not feeling comfortable. Then this is a point of interest. This is R vector, okay. So this depends only on theta. Phi didn't came at all, isn't it? Pick up. Like this, you just consider. So this was the sphere. You have placed Q charge here. Q prime you placed here. This was origin. Pick up. Z cap here. Is that okay? Somewhere here you are finding the potential. Am I right? Pick up. Italic R1, italic R2, like that, whatever I have taken. This is R vector, isn't it? Now if it is z cap, this is theta. This one rotated. And he's asking you to write this potential in the spherical polar coordinate, okay, by choosing this axis as a z axis. So then you will find that it is azimuthal symmetry. If you rotate about this axis, okay, nothing is changing here, okay, like that. If you rotate like this, in the potential, look at here, when you substitute these things back, only r and theta came, not phi, independent of phi. Okay, speak up. Just check that out. Now, okay, all of these are okay. Can you find the force? Speak up. Force of attraction. A minus B is the distance between them, right? Speak up. Force is equal to 1 by 4 phi epsilon naught, am I right? Q prime divided by A minus B the whole square, am I right? A minus B is the distance between them. And you substitute Q and Q prime. 1 by 4 phi epsilon naught. Keep Q as it is. What is Q prime? Minus R by A. What is Q prime? Minus R by A. Q. Okay. So A minus, what is B? R square by A into Q. What is B? R square by A into, no, R square by A, not Q. Okay, speak up. R square by A. Attractive force. Using spherical polar coordinate, he might have asked you to find what is the, what you call, surface charge density. By taking this one as a z cap. Speak up. Yeah. Now, in the actual configuration, V equal to 0 inside, am I right? V outside, you will find that one in the polar coordinate, okay? Again, what is this one? Sigma is equal to minus epsilon naught dou V by dou N. N is R here, okay? On the surface, if you want to find surface charge density, N cap is R cap, am I right? Speak up. Dou V by dou R, okay? Where R equal to capital R. Speak up. You'll write your potential in terms of spherical polar coordinate, right? Speak up. Inside it is 0, outside non-zero, okay? The discontinuity in the derivative will give you the surface charge density. This formula I have used in a quite different way, dou V by dou Z in case of that plane, am I right? Pick up. Using this one, you can find surface charge density also, okay? I don't think that's not too lengthy. If it is too lengthy, you can leave, but try that out, okay? I think here you will have negative charges, am I right? And here you will have positive charges. Isn't it? Pick up. Induced charges, isn't it? Check that out. Find this one. Find this one. Or at least if it is too lengthy, at least note down what is this one. It's a kind of cosine cosine function again. If this is theta, when theta is acute angle, okay, you have some negative of cosine, okay? You will have negative charge. When theta is obtuse angle, you will have positive charge in this part. Okay? Speak up. Yeah, do this problem. One more small problem solving session. That image problem is complete. Okay. Now next part, Cartesian and spherical polar, is to directly solve that Laplace equation with some boundary condition. Okay, for a given boundary condition. Okay, speak up. So now if you guys go through legendary polynomial and legendary differential equation, is better. Legendary polynomial and its property. From differential equation, I will ask him to share that one. Is that okay? I mean, it's not required. You can directly remember the solution. You have to directly remember the solution and apply the solution for a given boundary condition. Generalized solution, whatever we find. I mean, first for any differential equation, we first find the generalized solution. After we put the boundary condition, isn't it? Then we'll get a specific solution. Like that, you have to remember. But still, if you can go through the legendary polynomial, it's better. Okay, speaker. Yeah, we'll meet in the evening. Is that okay? Any question on Google Meet?